This is 11.2 on series. So they start us off with the definition. They say let S of n denote this sum, and if the sequence S sub n is convergent, then the limit will approach a finite number, and we'll call it convergent. Otherwise, we'll call it divergent if the limit does not exist. So let's start down here where it says calculate the first 8 terms of the sequence of partial sums, and then they want us to say whether it appears to be convergent or divergent. So let's start off with S sub 1, which is the first partial sum. So that's going to equal to the very first term, right? So if you substitute 1 in for n, you're clearly going to get just 1, because the cube root of 1 is 1, 1 divided by 1 is 1. So now let's start with the second partial sum, which would be the first partial sum plus the next term. So the first partial sum is 1, plus the next term is when you substitute 2 in for n, so it's going to be 1 plus 1 over cube root of 2, which if you do that on your calculator, you will get approximately, so I'm going to start using approximation, the symbol for approximation. They want 4 digits, so 1.7937 if you do that on your calculator, and so on and so on. The third partial sum is going to equal to the second partial sum plus the third term, which if you do that on your calculator, this is going to equal to 1.7937, plus if you substitute 3 in for n, you're going to add that term to this, and that will give us, let's see, a 2.4871, and you just keep repeating this process. So the fourth partial sum will equal to the third partial sum plus the fourth term, which is going to be equal to 3.1170. S sub 5 will be S sub 4 plus the fifth term, which will be 3.7018. And we have to go up to 8 for this. S sub 6 is S sub 5 plus 8. Whoops, that should be, yeah, that's correct. Plus the sixth term, which is going to be 4.2521. 7 is going to be S sub 6 plus the seventh term, 4.7749. And finally, the last one, 5.2749. So now you're supposed to look at the sequence of numbers of partial sums. Notice that this sequence starts with 1, and then the next term, next term, next term, so on and so on. Does this appear to converge to you? It doesn't appear to converge to me because the numbers are just getting larger and larger and larger and larger and larger and larger. So this appears to be divergent. Appears to diverge. So that's all they wanted us to do for that first problem. All right, so let's move on to the next one. So they define what a geometric series is. We kind of looked at this last class, or last section, but essentially if you have something in this form, then it's convergent if the absolute value of the common ratio is less than 1. And if it is convergent, then you can find the sum of the series by using this formula. If r, absolute value of r is greater than or equal to 1, then it's divergent. So let's look at this, determine whether this geometric series is convergent or divergent. If it is convergent, let's find the sum. So first thing you want to notice is that the common ratio is going to be 3/4. That is, if you multiply this by 3/4, you'll get 3. If you multiply this by 3/4, you'll get 9/4. If you multiply this by 3/4, you'll get 27/16, so on and so on. So now that we know that the common ratio is 3/4, the absolute value of r is 3/4, which is less than 1, which means that it is convergent. And since it is convergent, that means we can find the sum. And the sum is given by the formula a over 1 minus r. Here it is. All right, a is the first term in the sequence, or in the series, which is 4. And r is 3/4. So I like to change the 1 to 4/4 to make the subtraction easier. So that's going to be 4 over 1/4, which is 16. Okay. For the next example, it says determine whether the geometric series is convergent or divergent. If it is convergent, find its sum. So we want to make the exponent n minus 1. So in order to do that, you're going to have to do a little trick. And that trick or technique is to multiply the top and the bottom by 4 to the negative 1. I have to do the same thing to the numerator and the denominator so that I can keep the fraction equivalent. And the reason I'm doing that is because if you have the same base, that means you add the exponents. So what I'm going to do now is combine the two bottom numbers. So since the bases are the same, you can add the exponents. So that's simply going to be 4 to the n minus 1 if you add the two exponents together. And the reason I wanted to do that is because now since these two have the same exponent, you can group that into one single fraction. So this is going to become 1/4 because that's what 4 to the negative 1 is. It's 1/4. So this can be written as 1/4 times negative 3/4 to the n minus 1. So this came from these two terms, and this became 1/4. All right, and so this is a geometric series, as you can see. It's in the correct form now of a geometric series. And so now our common ratio is negative 3/4. And since the absolute value of r is positive 3/4, and that's less than 1, that implies that this series is convergent. And because it's convergent, we can find its sum again using the same formula as the previous example. So a over 1 minus r is going to be a is the first term in the series, which is given by 1/4 in this case. 1 minus negative 3/4. That's going to be 1/4 over, I'm going to change the 1 again to be 4/4. And then the double negative becomes plus. So I'm just going to change this to addition. So that's going to be 7/4. And when you multiply by the reciprocal, you're going to get 1/7. So that would be the sum of that geometric series. Okay, let's move on to the next one. Determine whether the series is convergent or divergent. If it is convergent, find its sum. So usually when you see a problem that's kind of got two fractions like this, a series that has two fractions, it could most likely be a telescoping series. So let's see what that looks like. So let's write out the first few terms. So if you substitute the first term, which is 4, you're going to get 1 over radical 4 minus 1 over radical 5. If you plug in the next number, which is 5, you're going to get 1 over radical 5 minus 1 over radical 6. And you can clearly keep going. I'll do one more. So now I'm going to plug in 6, so that's radical 6 minus 1 over radical 7. And then dot, dot, dot. Let's just go up to n. So I'm going to call this the nth partial sum. So that's going to be 1 over square root of n minus 1 over the square root of n plus 1. So this would be the nth partial sum. And now you will see that these terms cancel, and you can envision all these terms canceling out, and what you will be left with is the nth partial sum is going to equal to 1 over radical 4 minus 1 over radical n plus 1, namely the first term and the last. Okay, and so by the definition, in the very beginning of the section, it said that if the limit of, you can find the limit of a series by finding the limit of its partial sum, and that's going to be equal to the limit. So in other words, this is going to equal to that. So put an equal sign. All right, so now we can find the limit of this new sequence. So the limit of the sequence is going to be, as n approaches infinity, of 1 radical 4 minus 1 over radical n plus 1. Well, clearly this is going to approach 0 because the denominator is going to be infinity and the numerator is a constant. So this will approach 0, and so we're going to get 1/2. And that is what our final answer is. And thus, it does converge. Okay. Now they're going to give us our very first test for divergence. So whenever you have a series like this, they're gonna be asking us a lot to test whether it's convergent or divergent. So this is our very first test that we're given, and this test is only going to tell us if it's divergent or not. So this is the way you determine it. If the limit of this sequence does not exist, or if the limit does not equal 0, then it is divergent. All right. Not to be confused by the limit of a sequence. So for example, when we took the limit of a sequence and let's say you got 2, we said it was convergent. But if you get 2 in this case, it would be divergent because 2 does not equal 0. The difference is that this is a series, not a sequence. That's the main difference. Okay, so see how we have a series, not just a sequence. So now we can apply this rule to see this test to see if it's divergent or not. All right, so we are going to take the limit of this, which we will call a sub n, or a sub k. Either one works. All right, so we're going to apply the test for divergence. We're going to take the limit as k approaches infinity of that a sub k. And of course, whenever you have this kind of rational expression, you can divide by the highest power of the denominator, which in this case would be k squared. So imagine dividing every term by k squared, k squared, k squared, k squared. You're going to end up with 1 over 1 minus 2 over k plus 5 over k squared. These two terms will approach 0, and so our limit is going to be 1, which does not equal 0. Thus, the series diverges by the test for divergence. So once you determine whether it's divergent or not, you do have to quote the test that you're using. In this case, we use the test for divergence, so you have to explicitly say that in order to rationalize your conclusion. All right, so that is that. Let's move on. Okay, here's another one. Determine whether the series is convergent or divergent. Once again, you see this rational expression. Even though it's got that natural log in the front, you can still use the same technique. So let's do it. So a sub n is going to be ln of n squared plus 1 over 2n squared plus 1. So now we need to take the limit as n approaches infinity of a sub n, which is the limit as n approaches infinity of the natural log all right. And one of the properties of the limits is that if you have a natural log, you can move the limit to be, you can take the natural log, you can take it to the outside and take the limit of the inside of the natural log. So you can rewrite this as the natural log of the limit as n approaches infinity of n squared plus 1 to n squared plus 1. And now we're going to divide everything by n squared since that's the highest power of the denominator. So we have the natural log of the limit of 1 plus 1 over n squared, 2 plus 1 over n squared, and these terms will go to 0, and so you're going to end up with the natural log of 1/2, which also does not equal 0. Thus, the series diverges once again by the test for divergence. Okay, and that concludes the section.